Hello everyone, we're looking at Module 4, Homework A, Tab 2, and this is Part 1, Speed at Separation Distance. So this problem involves two charges, where capital Q is greater than 0 and lowercase q is greater than 0, with masses capital M and lowercase m respectively. The charge lowercase q is released from a distance r away from the charge capital Q, which is held in a fixed position, and we want to calculate the speed v of r of the charge lowercase q at that separation distance r, assuming that only the electrostatic forces are acting and gravitational forces are negligible. So this problem is analogous with the gravitational case, but with the electrostatic forces instead. The electrostatic force is governed by Coulomb's law. The electrostatic potential energy between the point charges capital Q and lowercase q separated by distance r is going to be capital U sub uppercase E is equal to lowercase k times uppercase q times lowercase q. That's all they're going to be divided by r, where k is going to be Coulomb's constant, capital Q is the charge of the fixed object, lowercase q is the charge of the moving object, and r is the separation distance between the charges. Unlike gravitational potential energy, electrostatic potential energy is positive here because the charges are repulsive. Both capital Q and lowercase q are positive. So the kinetic energy of the moving charge lowercase q is going to be given by k is equal to 1/2 times m times, that does not look like a v squared, where v is going to be the speed of charge lowercase q and lowercase m is going to be the mass of the charge lowercase q. So we need to apply the principle of conservation of mechanical energy, which states that the total energy of the system, which is kinetic energy plus potential energy, remains constant if no external forces are doing work. And initially, the charge lowercase q starts from a distance of r from capital Q, and its total energy is purely potential energy since it's released from rest. At the initial separation r, the kinetic energy is 0, and the potential energy is going to be this right here. Therefore, the total energy at the initial point is going to be capital E sub lowercase r is equal to 0 plus k times uppercase q times lowercase q over r, which is going to be equal to k times q times lowercase q all divided by r. As the charge lowercase q moves infinitely away from uppercase q, the electrostatic potential energy approaches 0 as r goes to infinity. And at this point, all of the initial potential energy has been converted into kinetic energy. So at infinitely, the total energy is going to be E sub infinity is going to be 1/2 times m times lower v squared plus 0 is equal to 1/2 times m times v sub infinity squared, where v sub infinity is the speed of the charge lowercase q at infinity. So according to the conservation of mechanical energy, we're going to have, like I said before, E of r is equal to E sub, why did I write E twice? E sub infinity. Substitute the expressions for the energy. So we have k times uppercase q times lowercase q all divided by r is equal to 1/2 times m times v squared, v sub infinity squared. And now we have to solve for the limiting speed v sub infinity. So we can rearrange the equation to isolate for v sub infinity squared, and that's going to be 2 times k times uppercase q times lowercase q all divided by mr. And then we can take the square root of both sides, and then that'll leave us with v sub infinity is equal to the square root of 2 times k times uppercase q times lowercase q all divided by m times r. And the speed v sub infinity is of the charge at lowercase q as it moves. Sorry, let me reword this. I'm stumbling over my words today. The speed v sub infinity of the charge lowercase q as it moves infinitely far away from the charge is this right here.